Thank you very much for being here on a Saturday afternoon. It's always a pleasure and an honor to participate to these so-called Bohr seminars, and especially this year, which is a wonderful anniversary of Niels Bohr's major achievement. And so what I am going to focus on is about a consequence, I think, of an old discussion between Einstein and Bohr, which is a rapidly developing field whose name is quantum information. So first, I can show that quantum information is really a flourishing field, because if you Google quantum information, you find tens and tens of millions of entries. And I have selected a few which proves that it is really very important. First, there is a journal of quantum information. But also New York Times talks about quantum information, which proves that it is really important. There are institutes for quantum information in Caltech, in MIT, in Cambridge, UK. So clearly, quantum information is a very important field. And so the question I'm going to ask and try to answer is, how did it emerge? Where does it come from? And here I have, in my opinion, what is the starting point. It was a discussion between Einstein and Bohr, starting from this paper of Einstein, Podolsky and Rosen, can quantum mechanical description of physical reality be considered complete? The reply of Bohr, and of course Schrödinger putting his grain of salt in this discussion. And then we make a big jump until John Bell, and John Bell finds that entanglement is definitely different, and he proves it by a mathematical inequality. And finally another almost 20 years jump, and then smart physicists, and among them Richard Feynman, find that not only entanglement is different, but it is more, and it allows one to do things that you could not do before. So this will be my talk, a first part about the discussion between Einstein and Bohr in 1935. And this was the starting point of the notion of entanglement, then Bell's theorem, and then more recently quantum information. So let us start with the first part. So I will first present the Einstein-Podolsky-Rosen situation as it was presented by Einstein, Podolsky, and Rosen, although we have a more modern way of presenting it, and I will do that later. So the idea is the following. What Einstein and his collaborators discovered is that the formalism, the standard formalism of quantum mechanics, it was well established in 1935. So the standard formalism allows to have a wave function for two particles which can be written like that, but a simple mathematical transformation allows it to express like this, and we will see the consequence. So let us focus first on this representation, which is a representation as a function of the position x1 and x2 of the two particles. From this, you clearly see that the measurement of the position x1 can give any result, but if you find x1 for the first particle, you are sure to find x2 equals x1 minus x0. So measuring x1 tells you for sure what you will find as a position for the second particle if you measure it. Okay, and from this, if you realize that the two particles can be very far apart, so you have a big wave function like that, you have the axis x here, the two particles can be far apart, but if you find a position for the first particle, you know without even doing the experiment what you would find if you would find the position of the second particle. And from this, you can conclude, and it was the first conclusion of that paper, that the position of the second particle was determined. Because if you are sure of what you are going to find, there is no doubt in an ordinary way of thinking that it was determined. but on the other hand, the formalism which is here does not tell you from the beginning where is the second particle. And so Einstein, Podolsky, and Rosen conclude that the formalism is incomplete. But it's not the end of the reasoning. I think this is more than enough. But anyway, there was something else in the paper. And the something else is now they concentrate on the second expression, which is equivalent to the first one, but now you express the wave function as a function of a product of this and that, and this up of x1 is nothing else than e to the ip over h x1, which is a function associated to a well-defined value of p. And as soon as you see this expression, you see that you associate a well-defined value of the momentum of the first particle, which is p, with a well-defined value of the momentum of the second particle, which is minus p. And so we can repeat the reasoning, except that now we think of a measurement of p. So I have again the big wave function here, and I measure p. And what I know is that if for the first particle I find a value of p corresponding to that, then I am certain that for the other particle, which is far away, I have no idea where, I am certain to find that. Well, maybe the plot is not the right one. And so you can repeat the reasoning for p, because at the moment when you measure p on the first particle, the second one is far away, so you cannot influence it. On the other hand, you are sure of what you would find if you would measure it. So the momentum of the second particle is well defined, and you must complete the formalism. And of course, if you put the two reasoning together, you can remark that you can wait until the last moment to decide that you want to measure the position or that you want to measure the momentum on the first particle, which means that for the second particle, the momentum and the position are well defined, and of course, this is against Heisenberg relation. And so, a second time, they can conclude that the quantum formalism is incomplete. So, look at the date of this paper. This paper was received by Physical Review in March 1935, and so it was published in May, okay? And now, what was the reaction? Well, the reaction, first, there was Schrödinger. And Schrödinger immediately realized the importance of this notion of entanglement. And and it is Schrödinger, by the way, who invented the word entanglement, entangled. And you are going to tell me that Schrödinger was a German-speaking person. No, he was a German-speaking person, but he was already, because of the Nazis, he was already in UK at that time. So he wrote this paper directly in English, and the paper was communicated by Max Born at the Cambridge Philosophical Society. And so he invents the name, so he says by the interaction, the two representative, by representative he means wave function, psi function, okay, this is jargon. The two wave functions have become entangled. And then, very importantly, after re-establishing one representative, one wave function by observation, which means that when I look at the first particle, then I find a well-defined value for what I measure. This is what he means by re-establishing one representative. Then the other one can be inferred simultaneously. And there is this notion that it's something instantaneously happen about our knowledge of the other one. And then he writes that attention has recently been called to, and he refers to the EPRI paper. And his conclusion is this paper, that is my paper, Schrödinger speaking of that paper, does not aim at a solution of the paradox, it rather adds to it if possible, which means that Schrödinger has fully realized the importance of the reasoning of Einstein, Podolsky, and Rosen. Now, the other important reaction is, of course, the one of Niels Bohr. And the reaction of Niels Bohr has been described by Rosenfeld, who was working with him at that time, and Rosenfeld writes, this onslaught came down upon us as a ball from the blue. Its effect on Bohr was remarkable. Everything else was abandoned. We had to clear up such a misunderstanding at once. And then Rosenfeld elaborates and says that he cannot find a good way, so he goes to sleep, and then next day, there was no trace of the previous day's sharp expression of dissent. As I pointed out, Rosenfeld speaking, as I pointed out to him that he seemed to take a milder view of the case, he smiled. That's a sign, he said, that we are beginning to understand the problem. And the reply will be sent as soon as July and published in October. Okay, so you see it's a very fast thing. Now, what was the basis of Bohr's reply? It was totally different from what we have heard this morning. When Einstein attacked the Heisenberg uncertainty description with a double slit, as we have seen this morning, Bohr could point out a mistake. Here, there is no question of mistake. It's a question of interpreting correctly the things, but he does not find any mistake in the EPR reasoning. And so, as soon as the abstract of his reply, Bohr says a viewpoint term complementarity is explained in the paper, so it's the abstract of the paper, from which quantum mechanical description of physical phenomena would seem to fulfill within its scope all rational demands of completeness. Because the question is quantum mechanics complete? And then he says, yes, if we analyze the situation presented by Einstein, Podolsky, and Rosen, having in mind the notion of complementarity, then quantum mechanics described as much as is requested, and the basis of the reasoning is that complementarity allows one to avoid the problem in the following way. Since here we have to choose for the first particle between measuring x or measuring p, we cannot measure the two things for the first particle. He insists, for the first particle I have to choose. Either I measure x or I measure p, and because I have to choose, then there is no problem of completeness. I cannot know both the momentum and the position of the second one. Okay, so this is the basis of the reply, and well, this is what is written here. Okay, so that's it. Then what happened? You know what happened? Nothing. Nothing happened. The discussion attracted basically almost no attention from working physicists, and I think there is a very good reason for that. Of course, first, quantum mechanics was extremely successful, and using quantum mechanics, physicists could understand many fascinating things that they are not understood yet, understanding the chemical reaction and the chemical bonds, understanding the properties of matter, light, interaction, etc. And, well, maybe there is a little electronism in it, but quantum mechanics was terribly successful. But I think that there is another reason. For people who looked carefully into the paper of Einstein and the paper of Bohr and their discussion, they found that there was no disagreement between Bohr and Einstein on the validity of quantum prediction. It was only, the disagreement was only about interpretation. Einstein never disagreed on the result of the calculation of quantum mechanics. He just said, okay, the result of the calculation, my interpretation is different from the one which is known as the Copenhagen interpretation. And if you are a working physicist, okay, Bohr and Einstein are discussing, but they don't disagree on the way to use the mathematics. In your everyday work, you use the mathematics, so why care, okay? And so I think that there is a good reason why there was not much attention from a majority of physicists. And then the situation changed very much with John Bell. And in order to present what John Bell has achieved, I must first introduce the version of the EPR situation as it was introduced by David Bohm. And the reason why it is important to introduce a new version is first that it is easier to make the Einstein-Podolsky-Rosen reasoning, but also that in order to find Bell's inequality and to find what I am going to show you now, you need to have discrete dichotomic variables. In other words, Einstein and company were working with x and p, which are continuous variables, which can take any value. And it is very hard to derive anything equivalent to Bell's inequality with continuous variable. Technically, there is a possibility, but it's difficult. So this is why I will introduce this. So what do we have? Now we have a source. Well, when Bohm presented it, it was emitting two particles which were spin 1/2, but I will rather consider 2 photons. It's strictly equivalent, okay? So I have 2 photons, and what I will do on each photon, I make a measurement of polarization. What is a measurement of polarization? You put a polarizer, it has a certain axis. If the light is polarized along the axis, it will go out in the channel +1. If it is perpendicular to the axis, it will go out in the channel -1, and you do the same thing. On the other side, you measure the polarization of the photon U2 along the direction B. You can rotate the polarizer. Here you can rotate the polarizer, A, okay, and you get +1 or -1. This is what I call a dichotomic measurement, just like for a spin 1/2 particle, you have a Stern-Gerlach, and you can rotate the Stern-Gerlach. Okay. So what can you do if you have an experiment like that? What you can do is send a pair and look if the particle goes out here or there, and so you repeat the experiment, and you get probability to find +1 or -1 for your orientation A, to find +1 or -1 for orientation B. But you can do something which is yet more interesting, is look at joint probability. P++ of AB means probability to get +1 here and +1 here when the two polarizers are in orientation A and B. Okay, so up to now there is no EPR. Now the Einstein-Podolsky-Rosen type situation is the following. The wave function describing the polarization of the pair has this form. What does it mean? Even if you don't know quantum mechanics, you can very easily understand what it means. X is associated to a photon with a polarization along the axis X. And Y is associated to a polarization of a photon polarized along the axis X. Y, sorry. XX means 2 photons polarized like that. YY means 2 photons polarized like that. XX plus YY means something for which I cannot move my arms and show something. It's certainly not something like that. It's this and that simultaneously. In a sense, it's the same thing as a Schrödinger cat, which is dead and alive simultaneously. Simultaneously, like this and like that. This is a typical entangled state, okay? And once you have an entangled state like that, it's very easy to calculate the result of the calculation of quantum mechanics for what you get here, P++, etc. The first thing that you find is that the probability of single detection here are independent on the orientation, and in addition, it's always 50%, 50%. So the light looks totally unpolarized. Whatever the direction of your polarizer, you have always the same probability to get +1 and -1. It's totally unpolarized. Here also, it's totally unpolarized. But when you look at the joint probability, as predicted by quantum mechanics, you find, for instance, this. 1/2 of cosine of the angle between the two polarizers to the square. And I claim that this is a very strong correlation, and I show it. Let's consider a null angle between the two polarizers. The two polarizers are orientated along the same direction. So cosine has a value of 1, so P++ equal P minus minus equal 1/2. 1/2. Doesn't look impressive, but it becomes impressive if you compare to the result which is here. Because here, what do you have? Photon arrives here, and you have 50% chance to find +1 and 50% chance to find -1. But the joint probability to find +1 and +1 is also 1/2, which means that the conditional probability to find +1 here, if you find +1 here, the conditional probability is 100%. If you're not fully convinced, look, P plus minus equals 0, which means if I find +1 here, I have no chance to find -1 on the other side. So what do you have? Here you have something that looks random. Here you have something that looks random. But if you have +1, you are sure to have +1. If you have -1, you are sure to find -1. These are the strong correlation, as strong as the correlation which were here. So you can repeat the reasoning of Einstein, Podolsky, and Rosen. But before doing that, I need a little technical detail. I will use in my presentation coefficient of correlation of polarization. How do I define it? I define it in a totally classical way. Here, I have a random phenomenon. Here, I have a random phenomenon. For instance, I toss a coin, it's head or tails, okay? The coefficient of correlation is nothing else than the product of the random results. You have two random variables, which at the end appear classical. When it is a new apparatus, it's a classical random variable with value +1 or -1. So what you do, you look at the product of the random variables, average, minus the product of the average, so average of the product minus the product of the average, and you normalize as you should do, and you get a formula which is absolutely classical. Now you introduce into this formula the prediction of quantum mechanics, and you find a result which is this one. So this is a correlation coefficient as predicted by quantum mechanics, and you find that indeed if the angle is 0, the correlation is 1, etc., etc. So I will need this quantity. Now, I have a situation in which I have strong correlation. How can I understand? What kind of image can I give? What kind of microscopic image could I give to understand this correlation? This, in a sense, was the aim of the Einstein-Podolsky-Rosen paper. And the first question, of course, is can I derive an image from the quantum mechanical calculation? Everybody agrees on the quantum mechanical calculation, so why not try to find an image from the quantum mechanical calculation? Now, if you look at the most efficient way of doing the calculation, you have to face the fundamental problem that you have in entanglement, is that this wave function of two particles is a wave function which describes things in an abstract space, which is the tensor product of the space describing the first particle by the space describing the other particle. And this space is an abstract space. And of course, you can follow what happens, but the idea of a microscopic description, as Einstein, Podolsky, and Rosen was doing, is to have an image in our ordinary space. How can we get one? For instance, I like very much this citation, which is on the front page of a book of Asher-Perez. And Asher-Perez, there is no doubt, is a deep follower and believer in the Copenhagen interpretation of quantum mechanics. Anyway, he says quantum phenomena do not occur in a Hilbert space. They occur in a laboratory. So we would like to have a description which is not a description in an abstract space. We would like to have a description which is in the real space. And there is a possibility, just using the standard formalism of quantum mechanics, and I explain it to you. When I say following the standard formalism of quantum mechanics, I can show you at each time in which page of the book of quantanology you can find the good reference for doing the calculation. So there is nothing wrong in the calculation I'm going to present now. So what we are going to do, we insist on being on the ordinary space. And so for that, I will suppose that this polarizer is a little closer to the source than the other one, so that there is first a measurement appearing here. So we know, according to the result of quantum mechanics, that the measurement can give the value +1 or -1. So we get either +1 or -1, and now what should we do? Well, we should apply the famous projection postulate. So when I say projection postulate, it looks innocent. If I tell you that it is the same, that the collapse of the wave function, etc., it looks a little more impressive, but it is the same, in fact, okay? So what is this projection postulate telling us? After the measurement, we have collapse of the state vector. That is to say, the initial state vector is projected onto the eigenspace associated to the result. But of course, the projector is not the same for the result +1 or for the result -1. And so the result is here. What does it mean? I have done a first measurement with a polarizer in orientation A. If I find +1, it means that the first photon was found with the polarization along A. What this tells me is that immediately after this measurement, the second photon is found with the polarization along A. But if the first measurement gives me minus, which means orthogonal to A, then immediately after the measurement, the second one has a polarization which is orthogonal to A. And if you accept that, and you have to accept it because it's a standard calculation of quantum mechanics, then all the rest follow, because then the measurement on U2 is just applying the Malus law either on this one or on that one, and at the end you find all the results that were previously seen. So we have now, so you do it with the Malus law, and so we have now an image in the real space. But there is a slight problem. It is that the measurement on U1 seems to influence instantaneously at a distance the state of the second photon. Okay, if I find this, I have that for the second photon, but if I find that, I have that for the second photon. And of course, this was unacceptable for Einstein. And this is why, by a reasoning equivalent to that, they conclude that quantum mechanics is not complete. This was the reason for the title of the paper. Okay. Now, I told you that I have jumped until John Bell. Why? Because John Bell, in 1964, took seriously the point of view of Einstein, Podolsky, or Rosen. He said, okay, let us assume that indeed we cannot accept this apparently propagating faster than light influence, and let us accept that we must complete quantum mechanics. What does it mean? Well, let's suppose you are a biologist or a medical doctor, and you have observed that identical twins not only have the same color of eyes, but for instance, you observe that identical twins develop the same disease. What you would conclude is that the origin of that disease is genetic, and that the reason for the correlation between the disease of the first twin and the second twin, the origin of the correlation stems from the fact that they have the same genes. So he said, let us imagine that we complete in a similar way. That is to say, when the two photons are born here, when they are emitted from the source, they have a common property, common gene, we call it lambda, and this photon gets lambda along with him, the other one gets lambda along with him, okay? And now the result of the measurement here depends on lambda and the orientation, and the same on the other way. And with this, of course, we fully understand that it is possible to reproduce a correlation. For instance, we could think of two photons emitted with polarization like that. So they go here, if I put my two polarizers like that, boom, it will go up. It's correlated. If the next pair is like that, will go down, strongly correlated. So we have an idea that this should work, okay? So what Bell did is writing a very simple algebra reflecting this idea. So you have lambda for the photon, which is for a given photon pair, there is a certain quantity lambda, which is the same for the two photons. So the result of the measurement here, A, depends on lambda and also on the orientation. And I insisted that it must be a dichotomic variable, so it can take only two values, +1 or -1. Similarly, on the other side, you have a function, capital B, depending on lambda and on the orientation B, and can take the value +1 or -1. And of course, when I go from one pair to the next pair, lambda will change. So I must define the density of probability, rho of lambda, to say how the various, what is the frequency, what is the probability of each lambda, and this density of probability is positive and normalized as it should be. Once you have this function and rho of lambda, you can calculate anything, and in particular, you can calculate here the correlation function. Okay, so if you have a good idea for such a theory, you can very easily calculate that and check how it compares to quantum mechanics. So I give you a very simple example. The simplest example you can think of, which works pretty well. You think that the two photons are emitted with the same polarization, okay? Now you put a polarizer here. What you want is that when the polarizer is aligned with the photon, you get +1. When it is crossed, you get -1. And you have to put the frontier somewhere. Where do you put it? At 45 degrees, okay? So this very simple model, you easily write the expression for capital A and capital B. It is written here, you can check. And then what for the probability of the distribution of rho of lambda? Well, clearly the problem has rotational invariance symmetry, so you write a function which is homogeneous, so 1 over 2 pi. And you do the calculation and the result is beautiful. For 0 degree, you find the full correlation, like quantum mechanics. You see the blue curve is the prediction of quantum mechanics. For 90 degree, you find -1. -1 means a total correlation. The minus signs means that if I find +1 on one side, I find -1 on the other side. But this is very easy to understand. I have crossed the polarizer. So minus for the second polarizer correspond to parallel to the first one. And then in between, it's not so bad. So you say, well, such a simple model allows me to reproduce the most interesting feature of quantum mechanics. So, of course, it's not exact, but probably if I have a more sophisticated model, it will be able to reproduce with supplementary parameters lambda, like that, I will be able to reproduce all the results of quantum mechanics. As I told you, it was probably the prejudice of many physicists, thinking that if you insist, you can find a model à la Einstein that will agree with quantum mechanics. But what Bell discovered is that this is hopeless. There is no hope to find a model that will reproduce the prediction of quantum mechanics for all angles. You can reproduce it at 0 degree, 45, 90, but it cannot reproduce at all results. How does it work? So this is what is written here. Okay. How does it work? Starting from the very simple formalism, it's really simple algebra. It's high school algebra. Well, high school at least when I was at high school. I'm not sure. But it's really high school algebra. You can show that if the coefficient of correlation can be expressed with capital A, capital B, rho of lambda, etc., there is a constraint for this combination here. What is this combination? This combination is 4 measurements where I consider 2 orientations, A and A prime for the first polarizer, B and B prime for the second one, and I do AB, AB prime, A prime, B prime, etc., the 4 of them. And you do this combination. And if the calculation of the E, which are here, follow the algebra of Bell, then this is restricted to be between -2 and 2. On the other hand, you remember this prediction of quantum mechanics for the EPR state, etc. If you take this value of the angle, which are plotted here, 2 times pi over 8 is, don't sleep, 2 times pi over 8 is pi over 4. Cosine of pi over 4 is 1 over root 2. Okay? Everybody follows? Good. So you have 1 over 2, 1 over 2, 1 over 2. Now what? A, B prime. Double the angle, the cosine is -1 over 2. Aha, but there is a minus sign here. So it's again 1 over 2. And so the result is that for this set of angle, quantum mechanics predicts 2 times root 2, which is obviously bigger than 2. So this is a demonstration that at least this is an example where a model as derived from the reasoning of Einstein, Podolsky, and Rosen doesn't work. Okay. So now the possibility to complete quantum mechanics a la Einstein is no longer a matter of taste or a matter of interpretation. It has turned into an experimental question. Is it less than 2 or is it 2 root 2 as predicted by quantum mechanics? And so, before checking, you know, when you have something which is conflicting with quantum mechanics, a so well-established theory, etc., it's not a bad idea to double-check what are the hypotheses leading to the conflict. And so, of course, there are tens, probably hundreds of papers arguing what do you need to have a conflict with quantum mechanics, what do you need to have Bell's inequality. I think that it is fair to say that the first thing you need is to introduce the idea of supplementary parameters carried along by each particle. This is what is called sometimes local realism a la Einstein. What does it mean? It means that when I have 2 systems which separate so that they are really separated in space-time, separated in the relativistic sense, everything you are going to find relative to the first system is described by properties inside that system. So lambda is with the system, and it will tell us everything about the result of measurement we are going to do on this system. And same thing for the other one. Then to derive Bell's inequality, there is a technicality that was emphasized by Bell. It's called the Bell's locality condition. It's the fact that the result of measurement here on the first system is not allowed to depend on the orientation of the other one. If the function capital A of lambda and A would also be allowed to depend on B, you could not derive Bell's inequality. Similarly, the way in which a pair are emitted, which is described by rho of lambda, is not allowed to depend on the orientation of the two polarizer, which is here. If you are a reasonable physicist, you don't think that what you do here depends on the setting of the polarizer, which is over there. But after all, how do you know? So Bell made the comment that in an experiment with variable polarizers, that is to say, an experiment in which you change the orientation of the polarizer while the photons are in flight, then, of course, the result on this side cannot depend on the orientation of the other one, because there is no time for a signal to tell that what was the value of the orientation. And even stronger, when the two photons are emitted, they don't know what will be the orientation of the polarizer later. And so the locality condition, which is written here, becomes a consequence of Einstein's relativistic causality if you can implement an experiment in which you change the orientation of the polarizer while the photons are in flight. So with this, I just repeat what was written. Now we have a conflict between really fully Einstein's ideas and quantum mechanics, and we can settle this debate by experiment. Okay, so I'm not going to describe in detail all the experiments. It would be too long. And I just want to say that there was several, I would say, series of experiments. The first series of experiments were the heroic pioneers, and the names are Clauser, Friedman, Fry, and it was the first series of experiments between 72 and 76 with a slight conflict, but the majority of the experiments were in favor of quantum mechanics. Anyway, if I would show you the experiment, the scheme of the experiment are really quite different from the ideal scheme on which we have made the reasoning here. And this is why I embarked in the mid-70s into a new type of experiment, the goal being explicitly to be closer and closer to the schemes of the ideal Gedanken experiment, and in particular, testing the quantum locality, which means really separating the measurement on both ends, okay? And then there was a third generation of experiment. I will evoke it also. So to make a long story short, the experiment we did here in Institut d'Optique, and at that time it was in Orsay, and at that time it was not such a nice cafeteria, etc. But anyway, we could do good physics. The main achievement was the following. These are three levels in calcium, which had been identified by Clauser and Friedman as a set of levels very nice, because if you can excite the atom to the upper level here, the atom has no choice than delivering a first photon and then a second photon, and because if you look at the value of the angular momentum of the level, and if you detect the two photons in opposite direction, you can convince yourself quite easily that what you get is exactly the EPR state for polarization you are looking for. The problem is that the two levels which are here have the same parity, and you cannot excite directly like that. So in the previous experiment of Clauser, Friedman and company, what they did was basically excited towards some higher lying energy level and waiting. And there were many paths for decaying, and from time to time, just by pure chance, or by pure luck, there was this, but most of the time it was through other routes. So their source was very inefficient, photon U2 had no companion, etc., etc. Because of the progress in nonlinear optics, and in particular of the progress that were done here in the laboratory of Bernard Cagnac by Gilbert Grimbert and François Birabin, we learned how to make a direct excitation of such a level by using a two-photon absorption. You add a first photon and a second photon so that the sum of the two energies exactly meets the Bohr relation, okay? And now, although the two levels have the same parity, but each of the transition changes parity, so you go from plus to minus, from minus to plus, and you can do it. And now when the atom is here, the atom has no choice. The only thing it can do is deliver the two photons you want to have. And the result was absolutely unbelievable. Well, wonderful, I would say. Because if you look at the experiment of Clauser and Friedman, it took them hours and days of accumulating data to have a reasonable signal-to-noise ratio. While here, the rate of observed coincidence was 100 per second, which means in only 100 seconds, less than 2 minutes, you get 10 to the fourth, which means a statistical accuracy of 1%. If you get a statistical accuracy of 1% in 2 minutes, you can do many tests and do many, many different things. So, apart from that, for the first experiment, the scheme was similar to previous experiments. So it was still quite far from the ideal experiment. Anyway, there is one thing that we did was pulling the polarizer far from the source. How far? As far as we could. The room was 12 meters long. After opening doors, there were 3 rooms, but if you open the door, it was 12 meters long. So one detector was 6 meters on one side, 6 meters on the other side. Why was it interesting? For the following reason. Some physicists thought that entanglement is a property of the microscopic world. So they would tell you, okay, in the helium atom, everybody knows that the 2 electrons are entangled. But you know, at large distance, entanglement will disappear. So we would say, and what is a typical scale for being at large distance? And the physicists would scratch it and say, coherence length of the photon. Okay, very good. Here, the coherence length of the photon was 1.5 meters. So this is why we pulled, and we were beyond the coherence length of the photon, and anyway, entanglement was still there at least as much as it was in previous experiments. And then we really fulfilled the program of being closer and closer to the ideal experiment. First, we implemented for the first time real two-channel polarizer, and for technical details that I don't want to discuss here, but as soon as you have really access to the +1 and the -1 result, which was not the case. In previous experiment, you had no access to the minus result, then it was more complicated. As soon as we had access to the -1 result, you can measure in a single run plus, minus, minus, plus, and minus, minus, directly measure the coefficient of correlation, and with this, we found unbelievably strong, a very impressively strong violation of Bell's inequality. I remind you that Bell's inequality tells you that the quantity S should not be larger than 2, and we find 2.7 plus this, which means more than 40 standard deviation. Remember that they announced the Higgs boson at 5 standard deviation, okay? So 40 standard deviation, there is no discussion. And then in the last experiment, we could implement switches sending light either towards the polarizer in orientation A or to a polarizer in orientation A prime, and the switch here was fast enough that it was equivalent to a single polarizer with the orientation change while the photon was implied. So here the violation was not so strong. Why? Because we lost a lot of signal, and after accumulating for a few hours, you think that it is enough. Then you are not sure of what you do. There may be systematic, but we found a clear violation by 6 standard deviation. So the conclusion was that Einstein's world view are untenable. Entanglement is as extraordinary as you have it in the pure quantum formalism, and there is no point in adding anything to the quantum formalism. There have been more recently a full series of new experiments, and there are 2 reasons for these new experiments. The first is that the experiment we did still has what is called some loopholes, okay? And the second one is that, and that's the most important, they developed a new source based on non-linear optics in crystal, and with this new source, the big benefit is the following. In our source, each photon was emitted in any direction of space. So you must collect the photon with a big lens and something like that. With such a source, the photons are emitted in a well-defined direction of space. So you can collect them and inject them into an optical fiber. And as soon as you can inject them in an optical fiber, you can go very far. For instance, Nicolas Gisin in Geneva is producing the photon here, and then he's sending the photon in the commercial optical fiber network of Swiss Telecom. Of course, he does it at night, but you know Swiss people sleep at night, so he can, they are quiet people, okay? So he does it at night, and while doing that, he found, for instance, that entanglement survives at distances of, I don't know, 30 kilometers or something like that. Anton Zeilinger, in a similar scheme, but done in a different way, also sent the photon here, and with this, he could do the experiment we had done, that is to say, changing the orientation of the polarizer when the photons are in flight, but in a better way. Why in a better way? Because the delay was long enough that he could choose the direction of the polarizer by working a random number generator. While in our case, we are just changing like crazy, you know, but we didn't have the luxury to have a random number generator to decide what will be the orientation, etc. Okay, anyway, he found, like in our experiment of 1982, he found a clear violation of Bell's inequality even when changing the orientation while the photons were in flight. Okay. There have been many other experiments for testing Bell's inequality, and as I told you, there is a question of loophole. So there were several loopholes mentioned in the literature and discussed by John Bell himself. The first one which was evoked was a locality loophole, but this one is closed by the fact that you change the orientation of the polarizer while the photons are in flight. But there is another loophole which has been closed only very recently by experiment done in Vienna and also in Urbana-Champaign, which is the following. The detector for photon, until recently, were detected with a limited efficiency. What do I mean? Well, for instance, a typical efficiency is, let's say, 30 or 40%. Let's say 50%, okay? Which means that you detect 1 out of 2 photons, but you lose the other one. And there were people insisting that supplementary parameter theory anyway are able to interpret the things, provided that the detector conspire against you by selecting among the photons. They select the photon which do violate Bell's inequality, but if you could detect all of them, then it would not violate Bell's inequality. This is why this recent experiment, in which the photons are detected with an efficiency, I don't know, 90% or something like that, this experiment closed that loophole. So I think there is no doubt that entanglement is definitely weird, and we have to accept this fact. Okay. Now, last part. Quantum information. We must realize, or we must be aware, that it took a very long time for physicists to recognize that entanglement is really something different in nature from all previous weirdness of quantum mechanics. And the best example, I think, is given by Feynman. If you look lectures on physics, everybody knows of this experiment in the spirit of what Serge has presented this morning, with a particle going through 2 slits, etc. And what Feynman writes, and we are in the late 50s, in the early 60s, in this chapter, we shall tackle immediately the basic element of the mysterious behavior in its most strange form. We choose to examine a phenomenon which is impossible, absolutely impossible to explain in any classical way, and which has in it the heart of quantum mechanics. In reality, it contains the only mystery. So what Einstein says, what Feynman says here, is that wave-particle duality for a single particle is the only mystery. And if you look a little farther, still in lecture of physics, he talks about the Einstein-Podolsky-Rosen reasoning, and he writes, this point was never accepted by Einstein and became known as the Einstein-Podolsky-Rosen paradox. But when the situation is described as we have done it here, there does not seem to be any paradox at all. So at that time, and I remember very well, when I started my PhD, many people would tell me that, okay, look, what you want to test is nothing else than wave-particle duality. And I had to tell them, no, I have two particles. No, but it's the same thing. Okay. Then, 20 years later, Feynman, in 1982, writes a paper in which I have some excerpts, but I encourage you to look into this paper. We, he means I, always, but you know, that's like a king, okay? Nous de majesté, exactly. We always have had, secret, close the doors. We always have had a great deal of difficulty in understanding the worldview that quantum mechanics represents. At least I do. And then he goes on, and a little farther, he makes this drawing. This drawing basically is measuring polarization of photon, etc., etc. He establishes in his own way inequalities that he does not call Bell's inequality because Feynman never cites anybody. So, but that's okay. He establishes inequality, and then this is what he writes. I have entertained myself always by squeezing the difficulty of quantum mechanics into a smaller and smaller place, so as to get more and more worried about this particular item. It seems to be almost ridiculous that you can squeeze it to a numerical equation that one thing is bigger than another, Bell's inequality. But there you are, it is bigger than any logical argument can produce. So, eventually, Feynman recognized that entanglement is another mystery. But Feynman being Feynman, as soon as he recognizes that, what does he do? He invents quantum computing. He says, okay, because entanglement is so different, we can do something with it, and he invents quantum computing. And so, now we have quantum information. The understanding of the extraordinary properties of entanglement has triggered a new research field, quantum information. The idea is that if you have hardware, you know, in standard computing, the idea is that all computers are equivalent. But they are equivalent because they are based on the same kind of physical laws. So the idea which emerged progressively is that if you have a hardware based on different physical principles, there should be new concepts in information processing and transport. So you have Feynman, you have David Deutsch for quantum computing, you have quantum cryptography introduced by Bennett and Brassard and by Eckert, you have quantum teleportation, quantum simulation. And entanglement is at the root of most of the schemes that you have here. I will just describe one because it stems very easily from what I have presented. The idea is the following. In order to communicate safely, Alice and Bob must have identical key. A key for encoding the message and a key for deciphering the message. It must be a similar series of +1 and -1 numbers. Must be absolutely identical, okay? And then, of course, you don't want that the spy who is here gets a copy of the key. Because if there is a third copy of the key somewhere, then everything is sent on a public channel. Okay? They code, send on a public channel, and decode. And if the spy has a copy, then they are in bad shape. But you remember what I explained you? According to quantum mechanics, and now we know that quantum mechanics is vindicated by violation of Bell's inequality, according to quantum mechanics, until the very last moment, you don't know if it is +1 or -1. And it is only at the moment when it is +1 or -1 here that you get a +1 or a minus in there. So the guy who is here cannot spy anything. There is nothing to spy in between. So that's the basic rule of the secret. Now, maybe he's so smart that he will make a measurement, look at the value, and then send a photon corresponding to the result he has found. So if he finds +1 along this direction, then he sends a photon with this. But by doing that, he makes a system that in fact, is equivalent to hidden variable theory. In other words, now, if Alice and Bob make a test of Bell's inequality, they are not going to violate Bell's inequality. So what Alice and Bob do, they communicate by open radio, and suddenly they say, okay, let us take the last 1,000 values that we had, and let us test Bell's inequality on it. If Bell's inequality are violated, it means that there was no spy on the line, because if there was a spy on the line, he leaves a footprint, and it is such, and he can be discovered by the fact that you violate Bell's inequality. So there are many other things, and I am going to stop soon. There are many other things in quantum information. There is, sorry for that, there is quantum computer. Quantum computer would be many entangled qubits. It's difficult to get a real number by specialists. It's more, nowadays, more often they say at least 1 million of entangled qubits. And the world record is 14, so it's far ahead, okay? So we don't know if a quantum computer will even work under this form, okay? But it would be a kind of Schrödinger cat. There is another branch which is called quantum simulation. This stems from the paper of Feynman. Feynman makes a back-of-the-envelope calculation, as we say, and he says, look, if we would like to describe in an ordinary computer a state of many entangled particles, it's impossible. The size of this computer would be bigger than the size of the universe. It's just impossible. So what can we do if we want to make a calculation of a large number of entangled particles? For instance, the electrons that you have in a piece of supraconductor or something like that. What can we do? One way is to replace the electron by something easier to observe and make a simulation of the situation. And this is an extremely lively field where we use cold atoms in optical potentials to mimic a situation describing, for instance, electron in matter. And it's a field which progresses rapidly, and I quantum era, and the two basic concepts are the following. First, entanglement. If you have not yet understood that I think that entanglement is important, probably you were sleeping, okay? But the other one that we should not underestimate is the fact that, in contrast to what physicists thought 50 years ago, Serge cited that, Schrödinger in the 50s, in the last decades, physicists have learned how to manipulate single atoms with the IFM microscopes, single electrons, single photon. Serge has pushed the manipulation of single photon to a wonderful art. And so I think that joining these two things, entanglement and individual quantum objects, when you look at all paper about quantum mechanics, it really seems that it puts us in a totally different world, and this is why we can think of a new quantum revolution. And so to conclude, who are the fathers of the second quantum revolution? Well, Einstein, who discovered a new quantum feature; Schrödinger, who realized that this quantum feature, entanglement, is really serious; Niels Bohr, who, in spite of the complicated words, and I apologize to Thomas for his grandfather, but we have to admit that the way in which your grandfather was explaining things is not crystal clear. Okay? The only forgiving thing for that is the following. You know, Niels Bohr once said that clarity and exactitude were complementary things. And it's clear that he wanted to be as exact as possible, okay? Well, we should not laugh too much. He was deeply convinced that if we use too precise words, he wrote also that, probably you have seen this text. He also wrote that if you use too precise words, then you don't render really an account of the truth, okay? But again, When you read his reply to Einstein, it's not easy. Anyway, reading and reading and reading and reading it again, I came to the conclusion that he had the intuition of something equivalent to Bell's inequality. That is to say that if you would accept Einstein's ideas and complete quantum mechanics along Einstein's ideas, then the quantum formalism would not survive that. He could not demonstrate it. It was Bell who demonstrated that, but probably he had the intuition. And of course, Feynman realized that entanglement could be used for something, and we stand on the shoulder of giants, and it's wonderful. And I would like to ask you a question. Do you know who wrote this sentence, "We stand on the shoulder of giants"?
Newton?
And?
Medieval.
Aha, you know, the real historian knows the story. Yes, of course, Newton. So here you have the answer. Newton wrote it, but he borrowed it from a medieval who was John of Salisbury. And you know why Newton wrote that? Because he was mean. He wanted to attack Hooke. And so Hooke was known to be a short guy. And this is what Newton wrote to Hooke. What Descartes did was a good step. You have added, speaking to Hooke, who is short, you have added much several ways, and especially in taking the colors of thin plates into philosophical consideration. If I have seen a little further, it is by standing on the shoulder of giants, meaning what you have done was not useful to me. Now, the real citation comes from John of Salisbury in the 12th century, who said, "We are like dwarfs sitting on the shoulder of giants. We see more and things that are more distant than they did, not because of our sight is superior or because we are taller than they, but because they raise us up, and by their great stature to us." Okay, I think with this I stop. Thank you very much.